Okay, so the previous lecture was about the fundamentals of state-based modeling, and we talked about basic concepts, states, state spaces. We checked out some operations and properties related to states and state spaces, and we learned about a formalism with which we can describe state-based behavior. It's called the extended Mealy automata or extended state machine formalism. I think we should overview this because this lecture is going to build on this. Okay, so here we have a state machine. And these rectangles represent stable situations, stable states of the model. And these arrows represent state transitions. So when we go from one state to another state, we can do this by executing such transitions. We can assign labels to these transitions. This label here, bottom one, represents an input event, a trigger to an input event. So this is the trigger. You receive an input event from this input channel, then this transition will be carried out. Of course, if the stable situation here is the lowercase state here, and after the slash, we can put outputs. We can emit outputs towards the environment. Okay, so this is the basic formalism that we're going to use today, and we're going to extend today. Okay, and the main idea is that we want to introduce hierarchical model refinement to these state machines. So the elementary states that I just showed you will be split into substates whenever possible. And the idea here is that this kind of refinement is something that we don't do without keeping the original state as well. Okay, so we will have something like this. So let's say we have a certain kind of activity, flavoring the tea, and we can split this activity into sub-activities, hanging in the tea bag, sweetening, stir. But we have to make sure, what we have to consider is that the time spent here flavoring the tea is the same time as we spend in these sub-activities altogether. Okay, so this is kind of an unfolding technique for these abstract states, for these abstract activities. Okay, and this will support compositionality. Okay, so this extension that we're going to check out today is called the state chart formalism. And a state chart is basically a state machine as we learned about it, plus we add state hierarchy, orthogonality, variables, and pseudo-states. Okay, we're going to go through these one by one. If you want to use such state chart languages, then you can use the Yak in the state chart tool. It's actually, I think it's free to use, but you have to ask for a license. Okay, so this is a good tool. And I think it's free for academia, so you will get a license if you say that you're from academia. The de facto standard of using state chart is via the UML and SysML modeling languages. I think most of you are familiar with SysML systems modeling language or the UML. So the unified modeling language, UML is mainly used for designing software systems, and SysML is used for defining any kind of system. And here we have the Gamma Statechart Composition Framework, which is a framework, an open source framework for the component-based design and analysis, verification of state-based systems. This is basically the product of my dissertation and my PhD. So I am the main developer of this, and we use statechart languages here to describe reactive behavior. As I said, it's open source. You can try this out at home. Maybe we will have a demo later this year using this tool. Okay, so we're going to start checking out these extensions, and we're going to start with variables. Okay, how can we use variables in state machines? So let's say we want to design an infinite counter using a state machine where we count the incoming tick events. So this is the state base. This is n, the set of natural numbers. This is what we would try to do using our previous knowledge on extended Needle machines. So here we have a state representing that 0 tick events have arrived. Then there is a transition here going to state 1 in response to a tick event, and then to 2 in response to a tick event, and again, so on and so forth. But the thing is that you can't really do this in practice, because whenever you use these states like this, you have to have, well, a defined number up until which you count. Okay, this is not something that you can define in a modeling tool. Okay, what we can do is that we introduce a variable, an integer variable, and you can consider this variable like a separate region. Okay, so basically using this variable, we're going to define this that you can see on top. Okay, so this is what we basically do. We have a count state. Okay, this is the initial state. When we enter this count state for the first time, this integer x variable is reset, and then we have a loop transition here triggered by the tick event, and whenever this loop transition is carried out, this x integer variable is incremented by 1. Okay, so what you have to see here is that these two things are basically the same, but this state machine is actually realizable in practice. Okay, you can see the correspondence between the transitions as well. So this one transition corresponds to all this transition here in the other state machine. Okay, and by introducing variables, we have to introduce this concept of state vector. So far, whenever we set state, there was a single stable situation in the state machine. So it was either 0 or 1 or 2. Okay, so now what we have is that we have these state nodes like count, and we have variables. And when we want to give this the state of the state machine, what we have to do is we have to give the state node as well as the valuation of the variable. Okay, because when we are in count, we do not know if what the value that this x integer variable holds. Okay, so this is called the state vector. We say that the count state node is active, and then the valuation of this x is 0. Okay, and upon a transition, okay, when we execute this transition, this x will be incremented. Okay, and we stay in the same state node. Yes, and actually this x variable can be considered as being in another region. Okay, so basically this x represents all these other state nodes here in the other region. Okay, so in addition to variables, we can also use guard conditions in state charts. Let's say we want to define a cycle counter. So the state space is 0, 1, so on and so forth up until a certain bound I. Okay, so similar to the previous one is that we do not count to infinity, but after I, we go back to 0. Okay, this is something that we actually define using these simple state machines, merely state machines. But the thing is, if we want to change this I value, then it's pretty hard to change this model. Okay, if you want to change this from 100 to 200, what we have to do is we have to introduce another 100 states and transitions like that, and we do not want to do this. Instead, in state charts, we can use guard conditions, and this is what we do. Okay, basically these two state machines are exactly the same behavior. So what we have here is we have a count state. We have two outgoing transitions. Both of these are loop transitions. And the new things here is that we have these predicates here, these Boolean expressions here within brackets right after the trigger. Okay, so we have these here. The thing is that for a transition to be executable, this predicate has to evaluate to true. Okay, so this transition can be executed if we receive an input event tick, and this x is less than I. Okay, and then we carry this loop transition out, and we increment x by 1. However, if this evaluates to false, this transition cannot be executed. So we have to have another transition here. It is triggered by the same event, and the guard condition here is that this x is greater than or equal to y. Okay, and the action here is that we reset this x, set this to 0. You can see that these are the corresponding transitions. So the orange corresponds to the orange transitions here, and the blue corresponds to this one. Okay, you can see this is much more compact. If you want to set, for example, this I bound from 100 to 200, what we have to do is that we just change the value here, I, and we do not have to introduce additional state nodes or transitions. Oh yeah, and in guard conditions, we can refer to variables, or if we have multiple regions, I'm going to talk to multiple regions pretty soon, then we can actually refer to those states of those orthogonal regions, these other regions that we use in the state machine. Okay, so we also have pseudo states, and the interesting thing about these is that these are semantically not states. So during execution, there is no time instant. There is no time instant when it represents the state of the system. So this is not a stable situation, but syntactically it is a state. So it is kind of a node on the state machine diagram. Okay, so it can be the start or the end state of a transition, so source node or target node of a transition. So we're going to check out two pseudo states. This one, the first one here on the left, is the initial state. The initial state must have a single outgoing transition, and this outgoing transition will denote the first active state of the state machine. This means that if we enter the state machine, we initialize it, and this count state will be active for the first time. Okay, and on the right, you can see the decision pseudo state. This can be used to define complex transitions. So this means that whenever in state count we receive a tick event, then in response we are going to enter this decision node, and there are two possible outcomes, this one or this one. You can see the outgoing transitions. The thing is that on the outgoing transitions of this decision node, triggers cannot be used. Instead, we have to use guard conditions. Okay, and whichever guard condition evaluates to true, the respective transition will fire. Okay, so if x is less than I, then this transition will fire. We're going to increment x. If x is greater than or equal to I, then we're going to reset x. Okay, these decision nodes can be used to create complex transitions, and actually they can be used in a subsequent manner as well. So the transition going out of a decision node can again enter a decision node where we can carry out another decision. Okay, so this model defines the same behavior as this one. But the thing is that this tick part here, okay, in this model, both of these transitions are triggered by this tick event. This is duplicated here. And here we do not have to duplicate this. There's a single transition leaving this count state triggered by tick, so it's easier to handle this. We do not have to duplicate parts of the model. Okay, so we are going to move on to this calculator example, and we're going to introduce hierarchical states in the context of this calculator example. I'm sure you have all used calculators in your life. So let's see what we want to model here. So we have to turn this calculator on. We press the on button. We press some digits here. Then we have a multiplication operator here. Digits again, and then after pressing the equal sign, we will get the result. Okay, and then we turn this calculator off. So let's see the state machine of this calculator. So this is the state machine of the calculator. You can see that this is a simple mealy machine, so we know everything here. We do not use variables here. We do not use decision nodes here. So everything is pretty simple so far. Okay, we start from the off state. You can see that this is the initial state, off state. And when we press on, we go to reading operand 1 state. Here we can press digits. This transition will handle these. And then if we press an operator, we go to reading operand 2, we press digits again, and then we can press the eval button and we display the result. Okay, the thing is that in any of these states, if we press off, we're going to go back to the off state. Okay, so this transition, and this transition. And in any of these states, if we press on, then we will go back to reading operand 1. Okay, so this kind of functionality, or these kinds of functionalities, are depicted by the orange and the blue colors. Okay, so this is what you have to see here. Regardless of the state here, if we press off, we go back here. If we press on, we go back here. And again, this is some kind of model duplication or code duplication. And we usually do not want to do this. We want to be able to express this in a more concise manner. Okay, so what we can do is that we can introduce super states, in which these super states, these common behaviors are captured. Okay, so we have this region here. We call this region. This is the super state, or hierarchical state, or composite state. Many people call it in different ways. Okay, and inside this super state, we have a region. You can see that we have the same states here, same substates now, reading operand 1, reading operand 2, displaying result. And the transitions between these substates, they're kept. And reading operand 1 is the initial state. You can see here we have this initial state in this region, and the outgoing transition goes into reading operand 1. So what you have to see here is these transitions here. So I said that regardless of which substate we are in, if we press off, we have to enter this off state. And you can see how easy it is to express this using this notation. Okay, and the thing is here that, as I said, this is not something that is exclusive here. So whenever we're in the on state, we're at the same time in one of these substates. So exactly one of these substates. So on and reading operand 1, or on and reading operand 2, or on and displaying result. Okay, so at the same time on and one of these substates. And that is why we can express this. So regardless of the substate, if we are in on, we can execute this transition triggered by off, and we're going to leave the substate, whichever substate we are in, and we're going to leave the on state as well, and we're going to enter this off state. Okay, similarly to this previous situation, we are in this on super state, and then on input event comes, then in response, what this does is executes this loop transition here. So first we leave whichever substate you are in, we leave the on state, and then we're going to enter this on super state again, even though we just left it, and we're going to enter one of these substates. And because this region has this initial state here, and the outgoing transition goes into reading operand 1, and this is going to be the first active state after entering the on state. Okay, so again, this and this is the same. The difference is that this representation is much more compact. We do not have to duplicate all these transitions that we have here. Okay, so the thing is now that we have hierarchical states, or super states, or composite states. The thing is that not only one state will be active during execution. Okay, so the first time when we enter the state machine, the off state will be active. So it's still pretty simple. This is just a simple state, no substates. So we say that the state configuration, the so-called state configuration of the state chart is off. And then in response to receiving an on event, we enter this on super state. We check in the internal region the initial state, the outgoing transition, and reading operand 1 will be active also in addition to this on super state. So we say that the state configuration of this state chart now is on and reading operand 1. Okay. If we have an operator input, then the state configuration will be on. Okay, we remain in the on super state because we're just in the region of the super state. So the substate will change reading operand 2, but we keep the on super state here. Okay, so yeah, as I mentioned, here we have two active states, and we talked about mutual exclusivity in the context of state spaces. But the thing is that a state chart is not a state space. Only states in the same hierarchy level can give a mutually exclusive set of states. Okay, but it will not be a state space either. Why? Because of the completeness properties. So when we leave this on state, then none of these substates will be active. So it's not complete. Okay, so what you have to remember is that from now on, in the case of state charts, we have state configurations because multiple state nodes can be active at the same time. Okay, here we have this ATM example. Probably you do not remember, but the idea here is the same. Here we have this customer authentication, selecting transition and transaction state nodes. And whenever we receive the cancel event here in any of these state nodes, we went to this idle state. Again, if we do not want to duplicate this functionality, then what we have to do is we have to introduce a super state, and then we have this transition here, leaving the serving customer super state, and regardless of what substate we're in, upon cancel, we're going to enter the idle state and leave any of these states. Okay, so we're going to introduce the concept of orthogonality in the context of this robot Hoover example. Let's see what I mean by orthogonality. Okay, so the thing is, we learned about this in the previous lecture. We might want to capture different aspects of the same system, different kinds of subcomponents, for example. So let's say we want to be able to capture the place of the robot Hoover. It can be on a pile surface or a flat surface or bed surface. And at the same time, we want to capture the mode of the robot Hoover, which can be inactive or cleaning. Okay, the thing is that this is a very bad notation here. Never use this during modeling. But for some reason, the drawer wanted to save some time and didn't have the time to create separate arrows for the separate transitions. Okay, so what we mean by these here is that we have a transition going from here to here and from here to here, and these are the two triggers. Okay, so pile surface, bed surface, there's a transition here if the Hoover goes into a bed surface represented by this W event. Okay, same for here. Inactive, cleaning, cleaning, inactive, in response to this deactivate and activate events. Okay, so the thing is that we want to represent both of these behaviors within a single state chart. Okay, so these are two different state machines, but state charts support this concept of orthogonality. So we can introduce so-called orthogonal regions, and we can represent both of these behaviors within a single state chart. Okay, so you can see that there is this dashed line here. This is what represents the orthogonality of this and this region. Okay, and the thing is that in every orthogonal region, during execution, exactly one state is active, one topmost state, because as I said, there can be super states or hierarchical states as well. So such a state could be hierarchical as well. Okay, but for the sake of simplicity here, we have simple states, and there is one active state in this region and one active state in this region. And yes, we have the state configuration concept that I already talked about. So we have during execution in this example, file service active here, inactive here. Okay, if we receive an activate event, then only this region will change. From inactive, it will go to cleaning. Okay, so the state configuration will be file service and cleaning because this region remained in the same state. Okay, so this was the basic idea. And the thing now that we want to check out is to support cooperation between such orthogonal regions, between such machines. And we're going to check out the main means or the main ways to create different kinds of cooperations using so-called product machines. Okay, so we're going to start with asynchronous products. Okay, we're going to check out asynchronous products of regions. Okay, so the thing here is that we have this orthogonal region here and this orthogonal region here. And the idea is that we want to create a single state machine, one region that is able to represent both of these behaviors, both of these states and transitions at the same time, but in a single state machine. Okay, so I want to be able to express that the robot Hoover is in file service and inactive at the same time, or file service and cleaning at the same time. Okay, so what do I have to do for this? We have to create these so-called product or composite states that represent states in every region. Okay, so I'm going to introduce a state representing file service and inactive at the same time, file service and cleaning at the same time. Okay, flat surface is inactive, flat surface and cleaning at the same time, and VAT surface inactive, VAT surface cleaning. Okay, these are going to be called product states or composite states in this sense. Okay, so very basically what we do is we create the Cartesian product of these states. Okay, so we have the states, and the next thing that we have to consider is that how to use these transitions. Okay, because I'm going to be express that I want to go from file service to flat surface, or file service to wet surface, or from inactive to cleaning. So the thing is that when we have these product states, we reintroduce transitions that represent only one of these transitions. Okay, so the thing is that this is why it's called an asynchronous product. Only one of these regions will take a step or will be executed when a single transition is fired. Okay, so this is the result. You can see that there are 3 times 2, that is 6 product states. This is what I said: file service inactive, VAT service inactive, flat surface inactive. So we have the inactive part here. We have file service cleaning, VAT surface cleaning, flat surface cleaning. So the cleaning is here. Okay, and you can see file surface, these 2, VAT surface, these 2, flat surface, these 2. Okay, so this is basically the Cartesian product. Then we reintroduce these transitions that represent only a single transition in the original state chart with the orthogonal regions. You can see that we have this P/P, V, W/F, P/F here, and only the surface changes here. Okay, from file surface to flat surface to VAT surface to file surface, it remains inactive. Okay, so when we represent these transitions in the new state machine, this part doesn't change. The right part doesn't change. It remains inactive. Okay, remains inactive. Okay, and when we have these changes, deactive and activate, then only this part, the inactive cleaning part, changes. Okay, deactivate, activate, inactive cleaning, and file surface remains the same. Here, flat surface remains the same, only the cleaning part changes. that surface remains the same, only the inactive and cleaning part changes here. Okay, so this is called the asynchronous product of these regions. Okay, so basically this is the first step that we do, but the thing is that these new models may need further refinement. So we say that when we are inactive, when we are here, then of course the robot hoover cannot change the surface. It cannot go from pile surface or flat surface or vice versa. So we have to exclude these transitions. We have to discard them in the refinement process. And as a result, states may become unreachable. This is not the case here, but in the future, keep in mind that after refinement, we may have to discard states as well because they are unreachable. Okay, so here we have the formal definition of the asynchronous product. So the asynchronous product of merely state machines is a composition operation over the component state machines, which are also called regions, orthogonal regions. The result of the composition is a merely state machine. The state space will be the direct product of the state spaces of the regions. Okay, this is basically, in this particular example, was a Cartesian product. The initial state will be every region in its initial state. And the transition rules are as follows. All transition rules are kept in which exactly one region makes a transition. This is called the asynchronity property. And all the other regions will keep their actual states. This is what I described here. So only one part, one element can change at a time. Okay, so here we have a very simple example. We have two regions, orthogonal regions, S2 transition triggered by E, and T1, T2 triggered by carried out by a transition triggered by an F event. Okay, and this is the asynchronous product of these regions. Okay, so what you have to see here is only one element changes. So upon event E, S1 changes to S2, T1 remains the same, or upon event F, T1 changes to T2, S1 remains the same. Okay, so there are other kinds of cooperation modes that we can use when we use state charts. How do we do this? This cooperation has to be carried out or modeled when we know that these two regions are not independent. Okay, so there is some kind of dependency between these two. And after the refinement process, we found out that we cannot change the surface when the robot hoover is inactive, right? So what we have to do is we express this in the model as well. And we can do this by means of guard conditions. Okay, so the condition of a transition in one region can use a reference to state in the other region. This is what I said when I said that in guard conditions, variables or state references of other regions can be used. Okay, and again, if a guard condition is present on a transition, then that for that transition to be fireable, this guard condition has to evaluate true. Okay, so these transitions will be enabled only if this in the other region this cleaning is active. Okay, so we have this asynchronous product machine again. You can see that corresponding to these guard conditions, we have this true or false guard conditions here. So these true guard conditions don't really say anything new. So if we have a guard condition, it has to evaluate it true for the transition to be enabled. If we have this true literal here, then it's always true. So no new information. However, here we have these false guard conditions. So these transitions will never be executable because the guard condition constantly evaluates to false. Okay, so we can discard, we can throw away these transitions. Okay, so this was one product. And there are two other product modes that we're going to introduce. The next one is the synchronous product. Okay, so let's say, as an example, we have a fridge with the compressor and the lab, and there's a common input, the input door event. Okay, it can open or it can close. We have two orthogonal regions. One is for the compressor, the other is for the lamp. Okay, here we have in the compressor region the cooling state, which is the initial state, and the idle state. Upon an open event, from cooling it goes to idle, and from idle it goes back to cooling upon the close event. Okay, and in the lamp region we have the initial state dark, so the lamp is off, and upon an open event it goes to light, and upon a close event it goes back to dark. Okay, pretty simple functionality. The thing is that we want to read the inputs together in both of these regions. Okay, this means that we have to carry out so-called synchronous steps. So what we do is, first we create a Cartesian product using these states. So we will have all the combinations here. So dark, cooling, idle dark, idle light, cooling light, so all the possible combinations of these states. And then what we have to do is we have to consider the transitions between these states, keeping in mind that they always carry out a step together. Okay, so the initial state will be cooling dark, of course, because here the cooling is the initial state, here the dark is the initial state. So in the product, cooling dark will be in initial state. We can see that there are outgoing transitions here from the dark and from the cooling as well, and they are carried out at the same time. So if we have an incoming open event, then from cooling we're going to go to idle, and from dark we're going to go to light. So both of these regions will have a change state. Okay. And now we're in idle, in light. Let's see the outgoing transitions. We have an outgoing transition triggered by close. We have an outgoing transition triggered by close here. Okay, so we're going to have idle light, and it will go back to cooling and dark. Okay, so upon close, they go back to cooling, dark. And again, the thing is that these are carried out at the same time. So both of these regions will change their states. Okay. What we see here is that we have, as a result of the Cartesian product, states that are unreachable. Okay, so we have cooling light and idle dark. The thing is that these are not reachable because all the time the states change at the same time. So it is not possible that, for example, upon an open event, this one remains in cooling and this one changes to light. Okay, so they change the states at the same time. This is a thing that you have to consider here. Okay, and another thing is that if one region cannot take a transition upon a certain event, then the other transition will not take it either. Okay, so it is not possible that only one of these regions will take a step. They always have to do this at the same time. And if one cannot do this, then the other one will not do this either. Okay, so everything is synchronous. They do everything together. Okay, so this is the definition of the synchronous product. So this is also a composition operation over regions. The result is a state machine. The state space, similarly to the asynchronous product, is a direct product of the state spaces of the regions. The initial state will be every region its initial state. And the difference here lies in the transition rules. We have transitions in which each region makes a transition at the same time. Okay, this is called the synchronity property. Okay, so what we do basically is we glue transitions together, they stick together. We have this union of the labels as well. Okay, so here we have this very simple example, S1, S2, T1, T2, transitions between these triggered by the event, and they carry out this step at the same time. So from S1, T1, upon event E, we go to S2, T2. Okay, and finally we have this mixed product construct. This will be basically the combination of the previous two, the asynchronous and the synchronous. Okay, so the product of the state machine will be achieved by composing the model from state regions, these components. So these regions can, as I said, represent components. The state space will be the direct product of the region state spaces, just like in the previous cases. The initial state will be the ntuple of initial states of every region, just like in the previous cases. But in the case of the transitions, we have a little bit of a change. Okay, so this basically will be an asynchronous composition. So most of the time, only one of the regions will take a step. But in some cases, the regions will act together. Okay, so this first one, basically an asynchronous composition, refers to the asynchronity property. And the second one, in some cases, the regions act together, actually corresponds to the synchronity property. Okay, so we mix these two. The thing is, we have to define these some cases when this synchronization can occur. Okay, the simplest form is that we consider common inputs. We have inputs that trigger transitions in both of the regions. And we say that these are the synchronization events. So when we have these events, we are going to have that both of the regions or all of the regions take a step together. In all the other cases, when only one of the regions can take a step, only one of those regions will take a step. Here we have this example. We have this microwave oven, and there are two components, the magnetron and the door. Okay, the door can be closed or opened. You can see the incoming events here that trigger the state transitions. And we have a magnetron here, which can be off or on. You can see that there are start, open, and these finish events here. These are the ones that trigger these transitions. Okay, the thing is that we talked about the full specifiedness of state machines in the previous lecture. The thing is that we can have states that have no outgoing transitions that are triggered by certain kinds of events. So in the other region here, in the case of magnetron, we have an input start event, but this one is not used in the door region. So what we do here now is that we imagine these invisible loop transitions. Okay, so if this one receives a start event in state open, then we imagine this loop transition here triggered by start. Okay, this is not part of the model, but this is how we kind of consider this. Okay, so how do we do this? Basically, what we do is create an asynchronous product here. So we have the Cartesian product of the states, open, closed, off, on in every possible combination. And then we define the corresponding transitions here. And first what we do is that we see that only open, okay, open is the only common event that is processed by both of these regions. So we're going to say that this is the one that will carry out, that will trigger the synchronization between these regions. All the other ones, so the start and this finish event and the close event, these will trigger asynchronous steps. Okay, so we define the corresponding transitions like in an asynchronous product. And the thing is that we only consider the ones triggered by this open event, because this is the synchronization event in this case. And you can see this one when we are in on in the magnetron and we are in closed in the door is when we have this synchronization. Okay, and this is the transition here. So closed, closed, on, and you can see that in every other case, only one of the elements change, so only one state in the corresponding region. And upon this open event, both the closed goes to open and on goes to off. Okay, so this is a synchronous transition, a synchronized transition. Okay, so we have this resulting mixed product, and the thing is, just like in the previous cases, you may have to carry out refinement because some transitions do not make sense. Okay, so for example, if the door is open, then regardless of what we want to do upon a start event, we do not want to go to on, right? So here we have this transition, even if the door, so if the door is open, we do not want to start the magnetron, okay? So this one doesn't make sense. This one doesn't make sense either for the same reason. Okay, so we remove these transitions in the refined models, and transitions may vanish as a result, and states may become unreachable as well. Okay, so here you can see that there is no incoming transition here in open in on. So what we do is we remove the state as well. Okay, and this is the resulting refined machine. Okay, so here we have this definition again. So the product of the state machine, we compose the model from state regions. The state base will be the direct product of the regions. The initial states will be defined by the initial states of every region. The transition rules are, well, basically asynchronous. It's basically an asynchronous composition, but in some cases the regions act together, and this corresponds to the synchronity property. Okay, and the simple case of synchronization is that if there are common inputs, then we call these synchronization events. The regions are going to synchronize over these events, or there's an advanced cooperation technique. An advanced cooperation model is called a rendezvous event. This is basically an internal synchronization event that we can use. Okay, we're not going to get into the details here, but just keep in mind, whenever you have such a mixed product in one of these modeling languages, you see these rendezvous events, this is what it means. Okay, the synchronization between the different components, the different regions. Okay, so this is the last slide. So we're going to overview these products, and then we're done for the first 45 minutes. So the product of the state spaces will be the direct product of the individual state spaces of the regions. So basically the composed states, the product states, are n-tuples of the states of the components. Okay, in each and every case, in all of these products. Okay, the product of the state machine, the state space is always the refinement of the direct product. You could see that we could remove some of the product states that we, for example, could not reach. Right, like this. Okay, so this is only the direct product, is only a potential state space. After refinement, we can remove some of these states. And the difference between the different kinds of products is that in the case of synchronous products, the regions take a step always at the same time. In the case of asynchronous product, the regions take a step always one at a time, so always one region changes its change. In the case of the mixed product, the steps are carried out sometimes at the same time, and sometimes one at a time. So it's a mix of this synchronous and asynchronous technique. Okay, and there are other modes of cooperation as well. So we checked out card conditions in the case of state charts. So in all of these products, we can use cards. And in the case of the mixed product, I talked about this rendezvous event, okay, which can be used to, in an explicit way, trigger the synchronization of multiple regions. Okay, so I think we should finish here. Let's take a 15-minute break. So we're going to continue at 9:18. If you have any questions, I'll be here for a few minutes. And after, well, the break, we're going to go through one of the exercises. So some exercises based on or for these concepts, these state machine modeling techniques, and maybe also state charts. Okay, I think we should continue with the lecture. So the second part of this lecture will be, well, basically a seminar. So we're going to go through exercises, and if we have time, we can go through another exercise, but I think we will have a single time for a single exercise. This is going to be this traffic light exercise, and we're going to use the basic concepts of the state-based modeling lecture that we learned. Okay, state space, state graphs, abstraction, refinement, and so on. Okay, so it would be nice if you had a sheet of paper and a pen, and you would try to solve these exercises alone, but I just don't think that we have time for this. So I'll try to be slow, so that when you have the exercise, the tasks, you can try to think about the solution. If you're very fast, you may even try to solve these kind of tasks, but I don't think that it will be feasible for each and every subtask. Okay, so first, traffic light. We're designing a controller mechanism for a traffic light. And the first task is that we have to create a state space for simple red, yellow, green traffic light that is detailed enough for controlling the traffic light. And we have to make sure that the state space is mutually exclusive and complete. Okay, what do these mean? What do these concepts mean? Complete means that always at least one of the states is active. And mutually exclusive means that only a single state can be, well, active or current in a certain moment. Okay, so if a set has these properties, then it is a state space. Yes, if both conditions are fulfilled in a set of states, then the set is a state space, yes. Okay, so what states can a traffic light be in? This is going to be a Hungarian traffic light. Actually, I've been here for more than 3 weeks. I'm not 100% sure if this is the case for Brazilian traffic lights as well. There may be minor changes or modifications. So this is going to be a Hungarian one. So red, this is true for Brazilian ones as well. And then there is yellow, green, and in Hungary we have this red-yellow phase, because in Hungary mostly we drive manual cars, and this red-yellow means that you have to, well, use the manual throttle and the transmission mechanism to put the car in the current state to move forward. Okay, so the red-yellow. Okay, we have another representation here. So this red means that the red is on and all the others are off. Yellow means that yellow is on and all the others are off. Okay, so this negation means that it's not on. Green means that the green is on and all the others are off. And red, yellow means that red and the yellow are on and green is off. Yeah, these are the states specified in the highway code, but the question is this set complete? So if we have such a question, then the answer is almost always no. So what else do we need? We can have this blinking yellow state. Okay, you can see very nice animation. I'm going to go back. So blinking yellow, see, it's blinking. Okay, it can be off as well. So none of the lights are on. Okay, the question is this mutually exclusive? Is this complete? Okay, we're going to check this out. Red, green. Do we need this? Well, no. Okay, so we can see that these are mutually exclusive. And we can say that it's complete. Okay, I'm not sure about Brazilian traffic lights. we have another other kind of state here, but for Hungarian traffic lights, this is complete. Okay, so this is the state space of this traffic light: red, yellow, green, red, yellow, blinking yellow, off. Okay, or we can use abbreviations. Okay, these are the corresponding abbreviations for these states. Okay, and this set of states is a state space again because it's mutually exclusive and complete. Okay, so moving on. Let's see that there are more possibilities. Okay, we can say that this traffic light is on. Okay, so there is an off state here. We can say that it is on, or we can say that it is working, or we can say that it exists. Okay, the thing is that these are also valid states for the traffic light, right? The traffic light can be on, the traffic light can be operating, working, the traffic light exists. But the thing is that these, if we include these states as well, then the set of states will not be mutually exclusive, right? So if it's on, it's either in red, yellow, green, red, yellow, or blinking yellow. If it's working in the main cycle, then it's in one of these four states. Okay, and the traffic light exists, then it can be in any of these states. Okay, so these are not mutually exclusive. But the thing is that we can have such combinations that are mutually exclusive. Okay, so we can say that the traffic light is either on or the traffic light is off. Okay, you can see that these are mutually exclusive. Okay, so maybe you are getting the concept here. So we're moving on to, so these on working exists states are going to be used later for state hierarchy, for defining state charts. Okay, so that is why we included these ones as well at this level, and to show the concepts of completeness and mutual exclusivity. Okay. Yes, so the thing is that depending on what we need, this could be a perfect state space as well. So on and off, depending on what we need, you know, this is called abstraction. We just only include those pieces of information that are of use to us. So from a certain perspective, to certain glasses, we might say that on and off, this is okay. Okay, this is enough for us. We actually don't care what actual state the traffic light is in. We're just interested in whether it is on or off. Okay, so abstraction again and refinement. Okay, so this is the results. So red, yellow, green, red, yellow, blinking yellow, off for now. And keep in mind that we have identified additional states that we will use later for state refinement. Okay, so this is the solution for the first subtask. So this is the state space that we're going to work with for now. Okay, so this is the second subtask. What are the state spaces of the individual bulbs? What is the abstraction relation between the state space of the traffic light and the state spaces of the individual bulbs? How does the state space of the traffic light relate to the Cartesian product of the state spaces of the individual bulbs? Okay, so first let's determine the states of the bulbs, then compare these with the light's state space, and last compare the Cartesian product of the bulb states with the light's state space too. Okay, so what are the state spaces of the individual bulbs? Okay, so let's say that we have a tree here that kind of occludes every light here apart from the red one here. Okay, so we can see that the traffic, the red light can be on. Okay, yellow, we do not see this right now. Okay, because we are checking the state space of the individual bulb. We do not see the yellow. Okay, so we have an X here. Green, same. Okay, we cannot see these. We're focusing on the red light here. Red, yellow. Okay, this is the other element in our state space. The red is on, right? Okay, and off. It is off again. Blinking yellow. It's off again. Okay, so in these states, red, yellow, red, this can be on, yellow, it's off, green off, red, yellow on, off, off. So what we basically do here is called a predicate abstraction. Okay, so the red bulb is on. It can be either a true or a false. Okay, this can either evaluate a true or false. Okay, so this is a predicate abstraction based on the original state space here. Okay, so now we have identified the two states of the individual red bulb. Okay, and this is the solution. So the state space of red is it's on or off. Same for yellow, on or off. For green, on and off. Okay, we're almost done. But we'll have to add the blinking yellow state too. Okay, so what we could do here is that this blinking yellow state could be the combination of the off and the the off and the on. But this would be quite cumbersome to handle. So for this yellow light, include off, on in this blinking state as well. Okay, so this is an addition here. Okay, so another question: what is the abstraction relation between the state space of the traffic light and the state spaces of the individual bulbs? Okay, we have this concept of projection. So when we have the state space of the original traffic light, what we do is basically we remove certain elements that we're not interested in. So we project to a single element, and this is the abstraction relation between the state space of the entire traffic light and the individual bulbs. Okay, so this is the state space of the whole traffic light: red, yellow, green, red, yellow, blinking, and off. So if we use a torch here aimed at the state space that is interested in only in a single thing, is the red bulb on, then this is what we'll have. Okay, we'll have the state space of the red bulb on or off. We have the same torch aimed at the state space in a way that it answers, is the yellow bulb on? And we will have yes, no, or this blinking state. Okay, and finally with the green. Okay, green can be on or off. So this is one analogy for projection using torches on the state space, focusing on certain things that we're interested in and discarding all the others. Another analogy could be using a certain kind of certain kinds of classes that subtract all kinds of light that we're not interested in. So we put on glasses that can actually collect the light of the red, of the red light, and discards all the others. Okay, so we put on the light and we see if the red is on or off. Okay, this is what we see. Same for the yellow. We could put on glasses that subtract all kinds of other lights except for yellow. Same for green as well. Okay, so this is another kind of analogy, okay, in addition to this torch. Okay, yeah, we have this nice animation here. So we have the original state space, and we have the state space of the red bulb. We say that this state space SR is an abstraction of S. Okay, this is an abstraction. We abstracted all the other elements here. So we can also change this. So S is a refinement of SR. Okay, so this goes both ways. So if one way is abstraction, the other way is refinement. Okay, we can also say that SR abstracts S refines SR. Okay, this is the same, is a refinement of or refines. So what you have to remember here is that if you say abstraction or refinement, it's not enough. It doesn't give enough information. You have to define the elements between the abstraction or the refinement is carried out. Okay, so moving on. So how does the state space of the traffic light relate to the Cartesian product of the state spaces of the individual bulbs? Okay, so we have SR, SY, SG, Cartesian product. This is a composition operation. We would compose these elements in all the possible ways, all the possible combinations, and this is what we get, the potential state space. Okay, this is all the possible combination that we can create from these elements. But the thing is that this potential state space is actually not the real state space. There are elements here that are not used. For example, red, yellow, green, they cannot be on at the same time. So we refine this even further. We discard the elements that are not of interest to us. So we will receive the observable state space. Okay, these are the elements that we identified in the first subtask. Okay, so what we say is this S is a refinement. The observable state space is a refinement of the Cartesian product of the state spaces of the individual bulbs. Okay, so here we have, yes, this decomposition technique. So if we have these elements and we decompose them by the states of the individual bulbs, we will have the original sets here. Okay, so this is the composition technique. Now, this is what I talked about in the previous slide in the context of projection. Okay, and yes, this is a composition. This is a composition operation. Okay, so we decompose the elements into the original sets. Decomposition, or this Cartesian product, this is a composition because we combine all the possible elements that we have here in the projected state spaces. Okay, so composition, decomposition, again, concepts that we introduced in the previous lectures. Okay, so now, what are the valid state transition rules? We have to create a simple state graph. Okay, so simple, really automaton, not a state chart yet. Okay, so we use these circles now to represent these states. Okay, many times in the case of finite state machines or merely automata, this is the notation that we use for states and not rectangles. Okay, we use rectangles for state charts. This finite automata, we have these circles for the states. Okay, so this is the off state. How does the traffic light work? So first we have to identify the initial state. And this is going to be the first state that is active after turning on the traffic light. Yeah, so the best choice here is probably the off state. And next we can easily identify the main loop of the light. At least for Hungarians, it's pretty easy. Okay, so we start from green. Okay, Okay, if we have green, we go to yellow. From yellow, we go to red. From red, we go to red, yellow. From red, yellow, we go to green. Okay, so this is the main cycle. The question is, can it go, for example, from red to red? Is it a valid state transition in the traffic light? And well, if we want to include this, then we can, but the thing is that it's not visible, right? So we have this red light can carry out this loop transition, but we will not observe anything from the output. So probably it's not worth adding this to the model. Okay, we do not add these soft loops. Okay, so moving on, the question is where to go after blinking yellow. Okay, this is not connected to anything yet. Where does it go? So from red, blinking yellow, we can go to green. But we can say that it would be a bad idea because at the crossing that would cause accidents, right? Because all of the lights could return to green at the same time. Okay, so this would be an option, but probably this is not a good option. Okay, the next alternative is red, because this would mean a safe situation, right? So blinking yellow, red, that's a safe situation. Okay, but maybe this is, well, we could say that too safe, okay? Sometimes when we have this blinking yellow light and if it changes to red very fast, then the cars would have to stop, and then that would cause sometimes situations that are not really good or not beneficial. Okay, so probably the best option here is going to yellow. Okay, so red is a safe state in itself, but this would mean a better transition because blinking yellow, it would go to yellow, and then from yellow it would go to red. Okay, so there would be this intermediate state here that kind of prepares the drivers for making a stop a bit later. Okay, so that's why we go from blinking yellow to yellow. Okay, another question, what is the initial state? So we turn on the light, which state we enter? Well, we could go immediately to yellow here too, but realistically it is better to go to blinking yellow. Yes, blinking yellow, because so this would not frighten the drivers. So turn it on yellow, and then we would go to this sequence again from blinking yellow to yellow and red. Okay, so this is a working state. This is kind of a compromise between this red and the green. So it prepares the drivers to, well, be alert. Also, there are questions. When can the traffic light enter the blinking yellow state? Okay, when we have accidents, there are certain kinds of faults, and there are certain kinds of planned shutdowns. Okay, so we can go from each of these states to this blinking yellow state. Okay, so that's why we introduced these transitions here. Okay, because these events can happen anytime in the main loop. So from where can we switch this traffic light off? Okay. If the shutdown is on purpose, then it turns to blinking yellow first. But the thing is that if you lose power, if you want to model that that we lose power, then you should introduce all these transitions as well from all the other states, okay, from the main cycle, in addition to the blinking yellow. So the thing is that we have to, again, focus on what we want to capture, what we want to model. If this is what we aim at, if we want to model this possibility as well, that the electricity is cut off, then we should include these transitions too. But the thing is that most probably, or most of the time, we can agree that this is a fault. We do not want to include this in the nominal model of the traffic light. Okay, this is not a nominal behavior. This is a certain kind of special situation or special behavior that happens in addition to, well, everything else that we want to include here. So we're not going to model these, okay? But keep in mind, there are different kinds of models that are tailored to this kind of stuff, okay? For fault modeling, okay? But in this particular example, we do not want to do this, so we want to capture the nominal behavior, the expected behavior of the traffic light. Okay, so this is the result of subtask C. These are the valid state transition rules that we have identified. Okay, moving on to subtask D, the question is, how can we represent the same behavior in a more compact way? Okay, and you can expect that now we're going to convert the state machine into a hierarchical one, into a state chart. Okay, so the first thing that we can see is that all of the states of the main loop have the same transition to blinking yellow. Okay, this one, this one, this one, this one, these red transitions. And this is the example that I showed you an hour ago in the lecture as well. So when we have this is a good indication, good indicator that there is some kind of common behavior here that we can express using a hierarchical state, super state. Okay, so we introduce this super state around the main loop, and we will be able to extract this transition and place it in between the super state and the blinking yellow state. Okay, and then we can also see that there is some kind of common behavior as well. And the common behavior that we want to capture here is that there are lights that are turned on. Okay, so here we have one state that represents the off state, and all the other states here represent that the traffic light is on. Okay, so this is a certain kind of other behavior as well. Okay, so by doing this is what we get. We introduce the working super state over the main cycle, and we introduce the on super state over the working super state and the blinking yellow state. Okay, and as I mentioned, now these are called regions. So the super states have regions, and the regions have to have initial states specifying the first active state when the super state is entered, and this will be yellow here. The working state, this will be blinking yellow here and on. Okay, and in the topmost region, the off is the initial state. Okay, yeah, so let's check out the elements. So this is an atomic state. Okay, there is no refinement here. There are no contained regions here. Okay, the on and working as well, they are complex states or hierarchical states or super states. Okay, and this is an initial state here, pseudo state. Remember that this is not an active, stable situation, so it doesn't represent stability. It seems like a state, but actually, semantically, it's not. We just use these to specify the first active state within a region. Okay, so when we turn this traffic light on, this off, so when we start executing this model, the traffic light will be off. And then when we turn this on, okay, we're going to enter the on state. We're going to check for the initial state inside the contained region. We check the outgoing transition here. So the first active state inside the on super state, the on complex state, will be this blinking yellow state. Yes, we have the transition between the working super state and the blinking yellow state. And this means that regardless of what state this region is in, this transition can occur. Okay, so it can be in yellow, red, yellow, green. If this transition occurs, then the corresponding substate is left, and then working is left as well. And then this blinking yellow will be entered. Okay, and we can have transitions going through hierarchy levels as well. So you can see that this blinking yellow state is not on the same hierarchy level as this one. Okay, on is on the same hierarchy level as off. Okay, yellow is inside on. Still, there's a transition from this blinking yellow to off. Okay, so we can use in state charts, we can use transitions going through hierarchy levels. Okay, so basically this is the result. And now let's try to organize all of the states in this hierarchy. Okay, so these are the states that we have here in the finite state machine, the colored ones. Now we introduced these ones as well, so off, on, working also exists. Okay, so we organize this into hierarchy. We can say that if we abstract everything here, then one state remains. This is exists, okay? But this is basically a stateless representation of any model, okay? So we can say for anything that exists, exists. This is the most abstract view of the system, okay? And then the next hierarchy level comes, so it can be this, this model can be either off or on, okay? So this is this hierarchy level, the topmost hierarchy level. Then on is refined into working, okay, working here, and blinking yellow here. Okay, and then we can refine this working even more into the main loop. So red, yellow, green, red, yellow, red, yellow, green, yellow. Okay. So again, what you have to remember here is that here exclusivity is not a thing anymore. So if the state chart is in red, then at the same time it will be in working as well and on as well. And of course, everything is in exist as well. Okay, so this is a state configuration, valid state configuration. If this state chart is in red, so red and working and on, all the states are active. Okay, and yes, here are the transitions that we can depict here as well. So these are the valid transitions between these states. Okay, this one. Okay, and the coloring also well, shows the correspondence between the elements here and here. Yeah, I talked about this, but maybe it's worth mentioning again. So another interesting thing is that in this state hierarchy, we have more than one state spaces. The root of this hierarchy is always a state. Okay, the system's only state like exists. Okay, this state is a state space in itself. Okay, exists, that's one element. It's complete and mutually exclusive because it's, well, basically it's the only element. So if we change to the children states, the substates, we get another state space. Okay, and we can do the same with this one as well. Here is another state space. And here we have the children. Again, we again get a state space. Okay, so basically this is how we symbolize or or create the connections between the hierarchical state machines and state refinement. Okay, so time is passing, so let's go to the next subtask. It's E. When measuring the electric energy consumption of the traffic light, we're only interested in the number of bulbs emitting light at a given time. We'll have to use abstraction of the current state machine to create a new one, where the states differ only in their energy consumption. Okay, so when we're in state off, then 0 light bulbs are on. Okay, this is what the 0 represents. In yellow, there is 1 bulb that is on. Red 2, 1 bulb. Green, 1 bulb. Red, yellow, 2 bulbs. Okay, and we're going to say half for this blinking yellow state, because half the time it's on, half the time it's off. Okay, so if we substitute the names of the states with these values, then we can see that we have multiple ones here. Okay, we have multiple ones here. These are the same state. So what we do here is that we merge these states into one state. Okay, so, and this is the resulting machine. So we keep this part, and then we merge these one states into one state. Okay, and then we add 2 as well. Okay, now we have to consider the transitions. So let's consider these transitions. We can get to half from 1, okay, because there is at least one state that has an outgoing transition that enters half. Okay, so we're going to have this here, this blue transition. And then there is a transition that goes to 1 from half. Okay, we're going to need this in the abstract machine as well. Okay, blue transition. Okay, why? Because there is at least one transition that enters 1. So in the abstracted machine, we have to add this. Okay, there are multiple transitions. Okay, 2 transitions that go in between the one state. So we introduce these loop transition, okay, because, well, this is one state now, so we go from 1 to 1. This is how we can symbolize this in the new machine. But probably this is not, just like previously we discussed this is probably not interesting, because we will not be able to observe this from an external point of view. Okay, so we don't need this. Okay, if you want to do this, this could be a good solution as well. But from our perspective, it's not necessary. It would just would create more confusion, or it would be harder to analyze this model. Okay, and moving on to this one. So there is a transition between 1 and 2. So we add this as well. And from 2 to 1, add this as well. Okay, and there is one from 2 to half. So we include this one as well. Okay, and that's it. Okay, this is our abstract state machine done. So what we did is basically we merged these states, the same states, into one, and then we checked all the possible transitions that could go into or leave this particular state, and of course all the others. Okay, here we can compare this to the original. Okay, yeah, so 1 corresponds to the merging of the green, yellow, and the red states. Okay, so I think this will be the last subtask. We have 5 more minutes, so let's get into this. At the end of the red signal, there's a period when the green bulb of the perpendicular pedestrian crossing is blinking. We have to refine the state graph, well, from before the abstraction in a way so that this state is presented in a separate way. Okay, so get the animation. Oh, sorry, yeah. Okay, so we're going to refine the state. Okay, so that's why we made this bigger. And this red state hides the circle states for now. These states are red and pedestrian green. Okay, we're going to represent it this way, in red and pedestrian blinking green. Okay, maybe in real life we would have a red and red pedestrian red as well for safety reasons, but let's keep it simple for now. Okay, from yellow, we could go to red and green, green or to ped, or both as well. So, so the thing is that how many possible answers exist in this way. So, yeah, this is what we want: yellow, red, yellow, and we have this blinking yellow, and this refinement kind of thing. How we connect to these possible original transitions this way. Okay, this is what we want to find out now. Okay, so one answer is that from yellow, and we enter red, we enter this red-green state. This is one possibility. Or there is another possibility that we go to red-green blinking. Okay? Or another possibility is that we do not choose in an explicit way right now, but we model both these behaviors at the same time, so introduce some kind of non-determinism. Okay, so this is 3. Okay, we can go into one, we can go into the other, or we can go into both of these. So we have a 3 here. And we can say the same about the 2 other transitions as well. So we can go from yellow blinking from red-green blinking, or both. Okay, and same for here as well. So we can go here from here, or from both of these. Okay, that's why we have these 3s, multiplication 3s. Okay, and another question: do we want to include a self transition here, a loop transition here in the case of red? And yes, depending on what we want to model, we could do this. If we want to do this, and we could do this as well, or this as well. So we have 4 additional answers as well, and the possibilities. Okay, so we have 0, 1, 2, or both. Okay, so that's why we have 4 here. Okay, so the possible answer is 108. Okay, because we have to combine them in every possible way. We have to multiply these values, so 108 is the answer. Okay, so moving on. We're going to stay with this solution. Okay, this is one solution. So the optimization, the thing is, yeah, so what this subtask wanted to show is that the automatization of state abstraction is pretty easy, pretty much automatable as possible. But for refinement, this is rarely true. So if you are the designer, you are the one who has to pass on your concept about the system, because without that, we can't choose the right model. Okay, we don't know which one to choose. When we want to refine this red state, we can have 108 possibilities. So the designer has to choose this. Yeah, what you have to contrast this with is that when we have this abstract state machine here, we had only one solution. Okay, so abstraction is trivial, can be automated using algorithms. When we refine some kind of behavior, then there are possible answers, possible solutions, and the designer has to use they had to come up with the right solution. Okay, and this is the very last one. It's very easy, actually very short. So let's go through this one. There are 10 traffic lights along the road, 4 states each. How many states can the whole system have at most? Do we have to handle every state? So what we have to do is that we have one traffic light with 4 states, another one 4 states, another one 4 states. Okay, and we combine all the states in every possible combination. So we have this, the 10 times. What we have to do is we have to multiply these values. So we can see that there are 10 factors for the elements, so it's 4 to the power of 10. So this is the result. Okay, this is a pretty big number. It's equal to 10 to around 10 to the power of 6, so around 1 million. Okay, do we have to handle every state? This is a question corresponding to the potential state space. So this is the potential state space. And of course, in real life, we have more information of the system. We know that the potential state space is many times not the real state space, and most of the time, this will be the thing here as well. So probably the real state space, the observable state space, will have a cardinality that is less than this. Okay, so this is the end of this seminar. Thank you very much for your attention. I actually used a little bit more time, 3 more minutes, but I hope this was useful. If you have any questions, feel free to ask. I'll be here for a few minutes. You can type them in the chat as well. Send emails as well, or of course, András will come in a few minutes and you will continue with process modeling. So if you have questions later, you can ask him as well. Okay, so thank you very much for your attention. Thank you for the nice words. Again, if you have questions, you can ask later as well. You can send emails as well. And as I said, my PhD was on the topic of state charts and state chart composition. So if you're interested in industrial applications, you're interested in maybe research applications using this Gamma tool, feel free to ask, because I've been working on this for the past 5, 6, 7 years. So I'll be happy to collaborate as well. I'm going to send you the link in the chat. Okay, so thank you very much for your attention, and I think András will come and continue with process modeling in around 10 minutes. So I think you're going to start at 10:15. Bye.